Hello, everyone. I am Reza Said Khandezi, and today we are going to discuss about the IEEE 802 standards, which particularly focuses on two dominant technology, the Ethernet and Wi-Fi in the communication system and network system. We are going to talk about the historical, architectural, and functional layer of specifically IEEE 802 Part 3, which covers the Ethernet connection, and IEEE 802 Part 11, which covers the Wi-Fi connection. Now, basically, Ethernet was initially developed by Robert Metcalfe uh, as a wired version of the AlohaNet wireless system. And the goal was to allow multiple devices to communicate over a single cable. The early versions of the Ethernet prototype were used. They are using a they were using a coaxial cable to connect the computers and operate at the data rate around 2.9 megabyte per second. It employed a carrier sense multiple access with collision detection. We call it CSMA/CD protocol, basically to manage the simultaneous transmission by sensing and resolving the data collisions. Now, the IEEE developed the first Ethernet standard in 1983 as the IEEE 802 Part 3. That standard were aimed to define the 10 base 5 physical layer, which we're using a thick coaxial cable for 10 megabyte per second communication. This standard introduced a shared bus topology that all the devices communicated over a single cable, which required a very careful timing, and it required to handle the collision. The standard that we are talking about, or 802 Part 3, specified the format of the Ethernet frames, which basically adopted the CSMA/CD for the medium access control and made sure a fair data transmission between all the nodes in our system. Now, when Ethernet transitioned from the coaxial to twisted pair cabling with 10 base-T, it basically made a more reliable and flexible start topology for the local networks. And the fast Ethernet, which was developed, the one we call it 100 base-TX, that version actually increased the speed to 100 megabyte per second, which was followed by 1000 base-X, which improved the speed to 1 gigabyte per second using the fiber and copper. And basically, the technology continued scaling like to 10 gigabyte Ethernet, 40 gigabyte, 100 gigabyte, 400 gigabyte, and recently 800 gigabyte internet. So it basically addressed the growing demands in the data centers and clouds. Now, the full duplex operation was introduced to basically eliminate the collisions by allow sending and receiving the data over a specific channel at the same time. We had another major innovation, which was auto negotiation, which made devices to automatically configure the highest common speed and duplex mode, which simplified the setup and ensuring the compatibility. Now, next innovation was Power over Ethernet, PoE, which allowed the Ethernet cable to transmit the electrical power, which were used to devices like IP phone and access point. Next innovation was energy efficient Ethernet, which reduced the power consumption when we had a low data activity by placing the physical layer into a low power ideal state. Now, we had also time sensitive networking as an innovation that was added to support deterministic communication that had ultra low latency, and it was for the application like industrial automation or autonomous system. Now, before the IEEE standards, okay, the evolution, let's talk about the evolution in Wi-Fi. Before the IEEE standards, the early wireless network were proprietary solutions used in a market like retails or healthcare. So these early systems operated without a unified protocol. Okay, basically made compatibility issues or limited scalability when we wanted to like deploy them in real world situation. Now, in 1997, the IEEE developed the first version of the 802 Part 11 and introduced a wireless LAN communication, which were supported speeds up to 2 megabytes per second. They were using the infrared or radio frequency to do that. That used two modulation techniques, either DSSS, which is the direct sequence spread spectrum, and FHSS, which is a frequency hopping spread spectrum. This standard basically created a foundation for modern Wi-Fi, and it did that by defining the key concept like basic service sets, MAC management, and frame type. Now, there were very rapid enhancements in the evolution of the 802 Part 11. There were so many revisions, B, A, 8, G, B, N. Each of them introduced a certain definition for different speeds, like the revision B basically boosted the data rates to 11 megabytes per second. Version A operated in 5 gigahertz band for a crowded 2.4 gigahertz device, supporting a 54 megabyte per second. Some of them actually was developed to support a specific technology, like the version AX supported the Wi-Fi 6, or version BE supported the Wi-Fi 7. Now, there are some key innovation in the wireless connection. One of them was the when the Wi-Fi used the CSMA/CA. The CA stands for collision avoidance instead of the /CD, because it was difficult to detect the collision over the air. So another innovation was the MAC layer evolved with RTS/CTS handshakes, and that happened to address the hidden node issues and enhance the timing and coordination mechanism. Now, we also had the innovation of like the security protocols were improved from WEP to WPA, then to WPA2, and now WPA3, which basically uses a robust encryption and authentication method. There were features like seamless roaming, fast transition, and adaptive rig scaling, which were innovated to enhance the mobility and user experience when we had a dynamic wireless environment. We had power-saving innovations like target wake time and sleep scheduling that basically allowed the clients to conserve battery life while staying connected in the networks. For example, Wi-Fi 6 use that. Now, both standards started with the shared medium protocol, both of those technology. And those short protocols was CSMA/CD for Ethernet and CSMA/CA for Wi-Fi. Now, both technology evolved rapidly at the physical layer. So transitioning from basic coaxial and DSSS to some sophisticated technology like fiber optics and like MIMO or channel bonding. And each generation basically gave us the improvement in bandwidth, latency, power efficiency, and scalability. So it addressed the growing demands of the modern technology and modern networking. There was backward compatibility, which was prioritized in both Ethernet and Wi-Fi, so it allows the newer devices to interoperate with legacy systems. This basically were done to protecting the users' investments and basically simplify the upgrades in the system. Now, there are some differences in these network evolution between the Ethernet and Wi-Fi. Like Ethernet evolved to deliver a deterministic, high reliable communication, which was very ideal for a structured and controlled environment. On the other hand, Wi-Fi was designed for mobility, flexibility, and user convenience. Ethernet achieved the higher speeds and capacity by advancing the cabling system, like introducing Cat5 and Cat8, or using the fiber optic. But on the other hand, Wi-Fi is scaled primarily by using new frequency bands like 2.4 or 5 or 6 gigahertz, and used more advanced modulation like QAM to increase the spectral efficiency. So despite those divergence passes, both technology basically were built to maintain interoperability and global scalability and forming the foundation of the modern networking. Now, there were some major innovation, like IEEE 802 reference model was developed to provide a structured and modular structure that help us to implementing communication protocols at data link, which we call it layer 2, or physical link, which we call it layer 1. The main goal was to make the communication behavior across different network technology become a standard, so we could make sure the scalability and flexibility across all the 802 networks. Now, that model splits into lower layers and 3 functional sublayers. Okay, so we have logical link control, LLC, media access control, which we call it MAC, and physical sublayers. The LLC sublayers is at the top of layer 2 and basically give us a uniform interface for upper layer protocols and hides the differences in underlying MAC and physical implementation. So physical layer implementation. The MAC sublayer is responsible for framing or addressing or medium access control or flow control. And it is significantly different between the Ethernet and Wi-Fi. The physical layer is further divided into 3 components. One is physical medium dependent that handles the transmission medium. We have physical medium attachment, PMA, which manage signal conditioning and clock recovery. We have physical coding sublayer, which performs the line coding and decoding for bit level transmission. Now, there are some benefits in that this layered and modular approach basically make it simple to design and implement network drivers and devices because each layer can be evolved independently. Now, it also promotes the protocol stack portability, which basically enabling the hardware and software to function across different vendors and platforms. This architecture provides a cross-platform standardization, which make it easier to deploy and manage diverse networks. And the model basically makes sure that the change or upgrade in one layer do not require a major change in the higher layer, which basically supports the long-term technology evolution. Now, we talked about the logical link control, the LLC. That LLC sublayer basically provides the interface, the standards interface between the MAC layer and higher level network protocols. It could be IP, ARP, or IPX. That LLC enables the protocol multiplexing by using service access points, SAPs. And basically this serves as a identifier to distinguish between the different upper layer protocols within the same data frame. Now, the LLC has a frame control, that handles frame delimitation and control field encoding. That could be the definition of LLC headers, which structure the communication between the layers in a kind of like a consistent and predictable way. The LLC optional reliability is also another characteristics of this logical link control. This operational reliability relies, which the system today rely heavily on that. And through that, the LLC can offer an optional acknowledgement and error recovery mechanism, which help us to be capable of operating in either connectionless or connection-oriented modes. Now, the function rule is another aspect which position above the MAC sublayer, and that part LLC, that characteristics of LLC makes the hardware-specific features of MAC and physical layers which enables a unified software interface regardless of whether the underlying network is Ethernet or Wi-Fi or another IEEE 802 protocol. In most of the modern TCP/IP networks, this LLC is implicitly bypassed when Ethernet typically uses the Ether type field and Wi-Fi using equivalent identifiers for protocol demultiplexing instead of a full LLC header. Now, we also introduced the MAC or Medium Access Control sublayer. Let's talk about the characteristics of that in Ethernet system first. Now, the MAC layer uses the CSMA-CD, and basically traditional Ethernet use that. In that kind of like particular kind of like situation, the device first listen to the medium before transmitting, and if there is a collision, they detect it and back off using a randomized algorithm. Now, the MAC for the Ethernet enforces a minimum inner frame gaps between the consecutive frame transmissions. We call it inner frame gap, as we said, IFG. That makes sure the timing synchronization and collision management. In another aspect, the Ethernet MAC transmits fixed format frames that could be a primable MAC addresses, type or length field, payload, and CRC for error detection. And in modern full duplex switching Ethernet, which CSMA is no longer needed because each device has a dedicated point-to-point link with the switch that eliminating collision altogether. Now, that MAC layer in Wi-Fi has also some characteristics. So Wi-Fi uses a CSMA-CA, which the devices listen to ensure the channel is idle, and then wait through a random backoff period before transmitting, and they do that to avoid collision, especially from hidden nodes. Wi-Fi also introduces request to send or clear to send RTS/CTS to mitigate the hidden terminal problem. And it happened where two devices can detect each other but interfere at a common receiver exists. Now, the IEEE 802 Part 11 MAC that defined that standard supports power saving mechanism also. It also supports the quality of the service prioritization and the mobility support. Wi-Fi defines three main frame categories. The first one is the management frame. The second one is the control frame, which supports medium access control. And the third one is a data frame, which carry the actual payload between the devices. Now, the MAC sublayer is the point where Ethernet and Wi-Fi basically diverge most significantly due to their fundamentally different physical media, and they require distinct access control strategies and timing coordination. Now, in the physical layer, we also have differences between the two technology, the Ethernet and Wi-Fi. For example, in the medium, in respect to medium, Ethernet uses the guided transmission media like copper or fiber optics, where Wi-Fi uses unguided media like radio frequency spectrum. In modulation techniques, Ethernet normally employs the modulation and encoding scheme like non-return to zero or RAM5 or PAM4, which optimized for high throughput and signal integrity through the cables. Now, on the other hand, Wi-Fi uses advanced RF modulation schemes like DSSS or OFDM. These are designed for noisy dynamic wireless environments. In respect to duplex mode, Ethernet supports both half duplex and full duplex. But on the other hand, Wi-Fi operates in half duplex mode. And because all the devices share the medium and cannot transmit and receive at the same time without any interference. Now, in the link negotiation perspective, Ethernet uses the auto negotiation, while Wi-Fi uses dynamic rate selection. The synchronization between the two technologies also different. Ethernet relies on a single-based clock recovery, when Wi-Fi synchronization is basically done through beacons, basic service sets, parameters, and timing synchronization functions, which basically coordinate access point and client operation through time slots. Now, excuse me, the IEEE 802 standards basically allow the physical layer upgrades, like moving from 10 gig to 100 gig Ethernet, without modifying the MAC layer, which basically make us to enable to scale the bandwidth without architecting the entire protocol stack. The MAC evolution is another aspect of the interoperability across the layers in this kind of like architecture. That MAC layer can be enhanced with new features without needing to retain this to change the physical hardware, so we can have the same physical hardware and preserve the compatibility and reducing the hardware replacement cost. Now, by maintaining a consistent logical link control, the LLC interface, the upper layer protocol can function identically across different MAC and physical layer implementations. And the backward compatibility basically makes sure that newer Ethernet or Wi-Fi devices can interoperate with older ones. As we said, it is very good for network upgrade and protecting the investment of the clients and the system. Now, the layer in IEEE 802, basically, they are designed to enforce modular independence. That means each layer can evolve independently. Because of the consistent inner layer boundaries, the network drivers and operating system software basically can support multiple hardware types, okay, with minimal adjustment. The IEEE 802 architecture also supports the cross-platform and cross-vendor interoperability, which basically enables us to have a diverse devices and communicate seamlessly regardless of the manufacturer. Now, there are some takeaways in the architecture of that IEEE 802. That IEEE 802 reference model basically serve as a specialized blueprint for layer 1, which is the physical layer, and layer 2, which is the data link communication, and is developed specifically to support the structure and function of the local area networks, the LANs, and wireless LANs, WLANs. The architecture is modular, as we said, meaning each sublayer can be upgraded and evolved independently. Okay. IEEE 802 basically enforces a clear separation of concerns between the sublayer in a way that logical functions are separated from physical transmission details. The MAC layer is where Ethernet and Wi-Fi basically has a significant difference because of the wired and wireless media, and basically impose a fundamentally different constraint on how device access the communication channel. Now, this model basically makes sure that the higher layer protocols operate independently from the underlying physical and MAC implementation, so it allows a consistent network behavior regardless of the medium and hardware. That modularity in IEEE 802 model allow us to have a network designer, allow us to the network designer to mix and match technologies, and they can do that while maintaining a coherent system. This architecture is inherently future-proof because innovation in one layer doesn't require redesigning the entire stack. So these are the key characteristics of the architecture in IEEE 802 standards. Now, let's focus a little bit more into each of those parts that we mentioned, the part 3 and part 11. Let us start with Ethernet, which is part T. As we said, the Ethernet began as a 10 megabyte per second shared bus system using coaxial cables. And through the years, it evolved to the highest speed as we have like a 800 gigabyte per second switch architecture over a fiber or copper. The Internet protocol is organized into well-defined MAC and physical component, which each sublayer having a specific responsibility and a standard interface. So we make sure the interoperability and scalability. Over time, Ethernet has achieved a very significant performance improvement in speed, reliability, power efficiency, and feature support. The Ethernet frame in the MAC sublayer basically includes of the structure fields like a Primble, start frame, delimiter, MAC source, and destination addresses, and like a cyclic redundancy check to help detection of the errors. The Ethernet uses a 48-bit MAC addresses for device identification and support a unicast or multicast and broadcast with a optional VLAN tagging. We have to also note that in a legacy shared medium networks, which Ethernet used the CSMA/CD for access control. But in modern full duplex switch network, this is obsolete because there are no collisions. Now, the MAC in the Ethernet enforces an interframe gap of 96-bit times between frames that ensures the proper timing and allow receivers to process the previous frame before receiving a new one. On the physical layer in Ethernet includes several layers. We talk about that: physical medium dependent, physical medium attachment, physical coding sublayer. It also has an auto negotiation that makes sure the device agree on speed and duplex mode before the communication begins. The encoding techniques in physical layer is different between different versions of the Ethernet. We have Manchester encoding, 4B, 5B, and 8B, 10B for fast gigabyte internet. We have PAM5, PAM4, and 64B or 66B for high speed links, and each designed to maximize data throughput while they could maintain the signal, the integrity. Now, physical layers has different medium used to be implemented. It could be a twisted pair copper cable. It could be fiber optics. It could be backplane connection. The link establishment in physical layer uses auto negotiation and link training protocols that allow them to identify each other and agree on compatible parameters, and also tune physical lanes for an error-free transmission. The MAC sublayer is where Ethernet and Wi-Fi, as we said, diverge very significantly. From the frame structure, the Ethernet MAC frame begins with a 7-byte primable and a 1-byte start frame delimiter. That helps receiver synchronize with incoming data streams. It includes a 6 bytes destination MAC address and 6 byte source MAC address. Also, a 2-byte type length fields follows which indicate either the payload length or the upper layer protocol. There is a payload field that carries the actual user data. And finally, a 4-byte CRC, the cyclic redundancy check, that provides a frame level error detection, which allows the receiver to detect transmission error. Ethernet uses a 48-bit MAC addresses format, okay, which enables a unicast, multicast, and broadcast communication. The VLAN tagging using an IEEE 802 Part 1 version Q basically adds an additional 4 bytes field after the source address, which segment traffic into virtual LAN. From the access control perspective, in Ethernet MAC. The MAC layer in a legacy shared media internet use the carrier sense multiple access with collision detection to manage the access by listening before transmitting and backing off after a collision. The collision windows and exponential backoff algorithm were applied into that to minimize repeated collisions on the shared bus. In modern full duplex switch networks or point-to-point connection, which eliminates the collision altogether, that a protocol that CSMA/CD is useless, and we can allow the continuous bidirectional data flow. And in another aspect, in another perspective, the MAC sublayer enforces an interframe gap of a 96 bit times, which means 9.6 microsecond at 10 megabyte per second speed between the frames to allow hardware to reset and prepare for the next frame. Okay, so from the physical layer components, 802 part 3 uses a copper or fiber and modulation scheme like NRZ, PAM5, or PAM4. However, the part 11 uses a RF spectrum like or OFDM. The subcomponent in the Ethernet physical layer is, as we said, is the PMD, which defines the electrical, mechanical, and optical specification for the transmission medium. The physical medium attachment is responsible for signal conditioning, clock recovery, and bit level alignment, which serve as a bridge between the raw physical media and the higher physical logic. The physical coding sublayer basically performs a line encoding, decoding, which enabling synchronization, DC balance, and error detection within the transmitted bit streams. That auto negotiation sublayer allows Ethernet device to advertise and detect supported speed and duplex modes, which make them select the best common operational parameters before initiating the data transmission. Now, in the physical layer, we have encoding techniques, which includes the Manchester encoding, 4B or 5B coding techniques. Another one is 64B or 66B, which increases efficiency while it maintains the alignment. For allowing higher data rates by transmitting multiple bits per symbol, we could use the PAM4, which is a pulse amplitude modulation with 4 levels. From the physical media perspective, Ethernet supports various transmission data. We already talked about them: twisted pair copper, fiber optic, backbone interfaces. From the link establishment, Ethernet devices initiate the communication using an auto negotiation and link training during the exchange capability which determine the optimal speed and duplex and adjust the physical parameter to make sure achieving a stable and error-free link. Now, in a full duplex system, which eliminate the collisions, MAC addresses learning in switches basically creates efficient forwarding paths. So each device receives dedicated bandwidth which enables microsegmentation. In full duplex Ethernet, device can transmit and receive the data simultaneously over a separated physical channel. Ethernet switches maintain a MAC address table, dynamically learn the source address of incoming frame, so it could make an intelligent forwarding decision. Because full duplex Ethernet provides a dedicated point-to-point links, there is no contention for the medium. And when a frame arrives at the switch, it looks up the destination MAC address in the table and forwards the frame only to the appropriate output port. Now, when we talk about the microsegmentation, basically the switching enables that microsegmentation, where each device gets its own collision-free segment. So we make sure dedicated bandwidth and consistent performance regardless of other network traffic. And by eliminating the collisions, basically we enable simultaneous bidirectional transmission, and using address-based forwarding, that full duplex switch in Ethernet significantly improve throughput, scalability, and latency throughout the network. Now, VLAN tagging adds 4-byte headers to identify traffic domains. PoE delivers power to end device. EEE allows physical layer to sleep. PTP and TSN provide a synchronized deterministic traffic for applications like AV and robotics. These are the advanced features of the Ethernet. So this is when the Ethernet become very kind of like advanced with the higher capability. Now, when we talk about the Wi-Fi, the Wi-Fi frame categories basically include management, control, and data frame. MAC address in the Wi-Fi uses, as we said, a CSMA/CA, and it handles the hidden node issues. Now, the Wi-Fi MAC layer organizes the communication in 3 primary frame types: management frame, control frame, and data frame. The Wi-Fi uses a carrier sense multiple access with collision avoidance. And when we talk about the RTS and CTS mechanism that is used to reserve the channel and avoid collision caused by the hidden nodes, especially when the environment has many clients and obstacles. The Wi-Fi supports power-saving mechanism where stations can enter a dose state and access points buffer data until the client wakes up. Wi-Fi also implements quality of the service using enhanced distributed channel access. Basically classifies traffic into 4 priority levels: voice, video, best efforts, and background. The Wi-Fi operates across 3 main frequency bands, which is 2.4 gigahertz for wide coverage, 5 gigahertz for higher throughput, and 6 gigahertz for ultra high speed. The physical layer in Wi-Fi uses some advanced techniques like OFDM, MIMO, channel bonding, or adaptive modulation. The Wi-Fi devices continuously monitor the link quality, interfaces, and signal strength, and dynamically adjust the modulation rate, the channel width, and the spatial streams, so it could optimize the performance in a changing environment. Now, the MAC sublayer in the Wi-Fi typically includes multiple fields. One is frame control, another one is duration ID, which indicates how long the channel will be reserved. There's address fields, which include source, destination, transmitter, and a receiver, depending on the frame type. We have sequence control that helps to detect and reorder duplicated or fragmented frames. We have frame check sequence, which provides an error detection at the MAC layer. The Wi-Fi also uses, as we said, CSM/CA. When a station first checks if the channel is idle, waits for the distributed inner frame space, then initiate a random backoff period before attempting to transmission, so it could reduce the collision risk and in the shared medium. Now that RTS-CTS mechanism reserved the channel by exchanging the short control frames, and it happened before the data transmission, as we said, which basically informs the nearby stations to stay silent during the exchange, which solves the hidden node problem when we have a dense wireless environment. Now, a station can enter a sleep mode or doze mode, so they could save some energy, and this is very helpful for increasing the efficiency of the devices and network. Now, when we introduced the Wi-Fi 6, the target wave time in that Wi-Fi 6 allowed the scheduled wake period, which clients negotiate specific wake-up times with the access point, which improves the battery life for IoT and mobile devices. The enhanced distributed channel access also classifies frames into 4 access category: voice, video, best effort, and background. Each of them has a unique contention window and arbitration inner frame space, which prioritize critical traffic. In the physical layer, in the Wi-Fi technology, Wi-Fi operates across 3 unlicensed frequency, as we said, 2.4, 5, and 6 gigahertz. The physical layer supports channels with like 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz, which wider channels basically have a higher throughput, but as a trade-off, it requires a cleaner spectrum and better SNR. Now, Wi-Fi also uses a variety of modulation schemes, okay? When each of those allowing a flexible trade-off between the speed and robustness, so we could choose which one we need based on our application and the characteristic of our system. The multiple input, multiple output, or what we call it MIMO, allows Wi-Fi devices to transmit multiple data streams at the same time over the same frequency, using multiple antennas, which significantly boost data rates and reliability. We have a multi-user MIMO, which is an extension to the MIMO, and allows the access point to serve multiple users at the same time, which also increases the spectral efficiency in an environment that we have very high number of clients. Now, IEEE 802 and Part 3 and 802 Part 11 are distinct, but also complementary. So Ethernet delivers high-performance deterministic wired network, when Wi-Fi brings convenience, mobility, and accessibility. Their architectural cohesion and interoperability basically makes them the dual foundation for the modern network. So this is the end of our discussion. So we finalized our talk about the IEEE 802 specifically for Ethernet and Wi-Fi. If you have any question, please let me know. Otherwise, thank you for your attention.